And we're back. All right, so we finished up last time by talking about electric field lines and the electric field. The electric field is kind of a map of where you would be pushed or pulled if you were an electric charge in a certain environment. And there are some rules for drawing the lines. And with these rules, you can draw the lines without any math whatsoever. That's the contribution of Michael Faraday. The rules for electric field lines are that they always go away from positive charges and towards negative charges. So that's great. Symbol here, word here. Good job, Harmon. They curve smoothly. They never cross each other, and the density of lines indicates the strength of the force you would feel. And if you really want to know how to draw them, you just say, hey, where would a test charge go? So I have some prepared environments, and I think we should draw some electric field lines for these environments. The first environment is two positive charges nearby each other. Now, this is not a dipole in the sense that we drew last time where there was a positive and a negative. This is just two of the same. It doesn't really have a name, but we can figure out that if you were a test charge and you were dropped off anywhere near one of these charges, the dominant thing you would feel, because of the rule that it's the distance squared, the dominant thing you would feel would be the charge that you were near. So we would have lines going away in all directions from, how many did I do? We'll just put another one there. Lines going away in all directions from this. And similarly over here, we would have lines going away in all directions from, I'll put another one in there, sure, that one. Now the question is, what happens if you're a little positive test charge and you get dropped off next to this guy? You get shot away, but as you move away from this guy, you begin to feel the influence from this guy, and he's repelling you as well. So your journey is going to bend, and you're going to go up that way. This one probably goes down this way. This one probably goes like this. This probably goes like this. In other words, this one's going to be pushing you away. This one's going to be deflecting you away from, let's see. Oh, don't do that to the paper. So I think that the electric field lines would look something like that from this guy. And then over here, similar thing. This would do this, this would do this, this would do that, this way, this way, this way. And we were just drawing lines going away and curving because of the influence of the other charge. So this is a pretty good map of what would happen if you dropped a test charge off in all kinds of different places and what it would feel. Notice that there's no lines in the middle here. The density of the lines determines the strength of the force. Well, there's no lines in the middle. Now, why would there be no force in the middle? Well, think about it. If I drop a test charge off here, it would be equally repelled from this guy, and it would just hover there. You drop it off a little above, and it would be mostly repelled either way with just a little bit of upwards push, so it would go that way. This is kind of a dead zone in the middle, and that's really reflected here in the drawing. All right, not the most professional drawing in the world, but let's take another step. Here's two negative charges. Now, pretty clearly, if I drop you off very close to the negative charges and you're a positive test charge, you'll be pulled in directly. So we expect inwards next to each of these. But what if we dropped you off way up here? Well, you would be attracted kind of straight down. Equal side-to-side attraction, but attraction towards the center. If you were a little closer to this one, you would be pulled in this way. So we get the exact, oh, good, okay, see, bad. I was not paying attention to my drawing skills. It's so much easier to go away from the charge than it is to come into the charge. We'll draw one more here. Okay, so we're going to have that kind of activity here. I'm just going to draw away because it is so much easier than drawing towards. Okay, and these arrows are all going towards because a test charge would be attracted. So notice it's the exact same drawing with the arrowheads going the opposite direction. Oops. Same. Arrows going the opposite direction. So that's what happens. That's fairly complicated to look at. Here's one that's a whole lot easier. What if we had a plate or a line of positive charge up here and a plate or a line of negative charge down here? Imagine a ceiling of a building with metal on it and the floor of the building with metal on it, and we charge up the ceiling with positive and negative. Well, if I drop off any test charges up near this roof, they're going to be repelled like crazy away from the positive charge and actually attracted like crazy to the negative charge. And if I dropped one off right there, let's say, it wouldn't go left or right because look, there's positive over here pushing it this way, positive over here pushing it this way. It would just go straight, perpendicular down. And as it turns out, this is true no matter where I drop off the charge. So the test charge, well, now on the edges we might have a little bit of an issue, but in the middle here we're going to have a whole bunch of field lines going down parallel to each other, perpendicular to the thing. Now, on the edge, you're right. If I drop the test charge off there, it would be attracted to the negative, but it would be repelled at first a little away and then come back in like that. So we'd get like a little fringing action on the edge, a little bowing on the edge. But in the middle, this is a very uniform field. Equal spacing, same strength top to bottom. This entire area in here feels the same electric field. This particular arrangement of charges, the parallel plates of opposing charges, is a very common thing to build things out of when you want a uniform electric field to happen in the middle. And if you ignore the edges, if you do make sure your experiment takes place in the middle, this can be pretty good. I had this idea one time of designing an astronaut training facility where we would levitate people by turning this diagram on its head, putting positive charge on the floor, negative charge on the ceiling, and then in this electric field, we would put an astronaut who wore some sort of suit that would make the astronaut positively charged. And if we adjusted everything just right, the amount of charge on the astronaut, the amount of charge on the ceiling and floor, we could have this strength of this electric field be exactly equal to but opposite the strength of the gravitational field. And a person could float around floor to ceiling in this area. That would be kind of cool. It's a little impractical in the sense that if the astronaut in this area was to somehow accidentally discharge, then they wouldn't interact with the electric field as much and they would fall. So I'd have to put some sort of safety net above the floor. But I've done the math and it can be done. But this kind of parallel plate arrangement produces a very uniform field. It's also true, let me wrangle some paper here. It's also true that if we just have the positive plate and we drop test charges off in the center, it's still true that it just moves away, okay? But more rapidly as you get away from the center, there's more positive charge on one side than the other, and it starts to bend a little bit. So this one is a little more bendy, still having a fairly uniform section in the middle before you start getting a little bendy, and then more bendy, and then probably lots of bendy. Like that. This would be what I would draw as an electric field. Again, very uniform in this area, but swirling away. You're just trying to get away from this positive charge. The further you get from this sheet of positive charge, the more it looks like a very small concentration of charge. It's like a single positive charge. So this is the electric field I would draw using the rules, and I would be able to see what was going on here. Now, as a final example, let's try this. Here is an attempt to kind of work this out and undo what happened in that previous diagram. Agreed, we put a sheet here, it's all done, it's even. But what would happen under these conditions? Well, clearly, in the center, a positive test charge dropped off right there would be repelled away from the positive, attracted to the negative, and would travel in a straight line. Dropped off over here, repelled away from the positive, attracted to the negative, probably would start off pretty straight and then curve in a little bit, and the opposite side would probably do the same kind of thing. And the further you get over here, the more that bending is going to take place. The more bending is going to take place. So we wind up making this kind of a, I don't know what you want to call it, like a bird cage shape, upside down bird cage. Maybe we even have one over here that swirls around like this, depending on the strength of the negative charge. So using the the rules of electric field drawing, this is what would happen in this geometry and arrangement. So that's how easy it is to use Faraday's electric field drawing technique to imagine and visualize the electric forces something would feel if there were charges. One last thing I want to say, because we're at the 10-minute mark. If you have a negative charge simply obeys the same lines, just in the opposite direction. So the field lines are drawn for a positive charge, but it's very easy mentally to figure out what would happen to a negative charge. All right, thanks again for your attention.